Welcome online lecture series in our wireless mobile communication lectures. In this series, we will discuss the different outdoor propagations model. We know that radio propagation models are empirical in nature. That is, these are developed based on the large collections of measured data or for the specific wireless communications environment. For any model, the collections of data has to be sufficiently large to provide enough likely to all kinds of situation that can happen in that specific environment. Like all the empirical models and radio propagation model do not point out the exact behavior of the link, rather than they predict the most likely behavior of the link that they may exhibit under the specific conditions. So what are these specific conditions? Suppose there is a transmitter and there is a receiver, and it is suppression distance in between is small d. So by natural and human made things are in between are lies to disturb the propagations between these two endpoints, like human made tall buildings, trees, lamp post, and natural rivers, or others phenomena which can disturb the propagation of radio waves to reach at the other points. So the different propagation models has been developed to predict this path loss over the irregular drain. So this is the irregular terrain, and one more condition is also affected to mode of propagations is the weather phenomena such as the rain, fog, dust, and snowstorms, air disturbances, and the significant difference in the temperature at different altitudes can affect the performance and reliability of the wireless link. So different propagation model has to develop to predict this path loss over this irregular drain. So some of the most popular outdoors models are like Longley Rice model, OKUMURA model, HATA model, PCS extension to HATA model. We know that the measurement of the transmission and the reception power and we have to plot this in graphical manner. So on the basis of this, we are now able to find out the what is the path loss So the radio transmission in a mobile communication system often take place over the irregular terrain. So the terrain profiles of particular area need to be taken into account for estimating the path loss. So in order to solve these problems, the terrain profile must be taken into the considerations for the estimation of your path loss. Trees, buildings, mills, hills, desert, water bodies, etc. must be taken into consideration. And outdoor radio transmission took place in this irregular terrains. So the outdoor model include your Longley rice model. So we need to uh, design some model. And what type of design? This design is nothing but is the practical link budget design using path loss model. So what we are going to design? So so practical practical link budget so practical link budget design practical link budget design using using path law. So under this heading, practical link budget design using path laws, we have to see over a simple uh, model for radio propagations, and on the basis of we are drive the two types of applying method, either empirical method or by using the analytical methods. So this approach uh, is valid uh, when we are using the analytical approach, because under this model we are actually driving the mathematical equations, and on the basis of this mathematical analysis we are seeing how much path loss is taking place. And this another approach is not taking, because it is the empirical method and it is the measure the curves, so which will not give a full information. The first Longley Rice model, also known as irregular drain model. This is also known as irregular terrain, irregular terrain model, and in a short form it is known as ITM. It is calculate the large scale medium propagation loss relative to the free space propagation loss over a irregular drain. So you can write it is calculates large scale calculate the large scale median propagation median propagation loss relative to uh, it is applicable to point communications, and also cover the in large rice model. It cover the around 40 megahertz up to 100 100 gigahertz. 40 megahertz to 100 gigahertz. It's covered the range, and it account for a wide range of the terrains. It is obviously, you have seen, if you using such type of wide range, so you also cover the wide area. So in this area you also cover the wide area of the drains. So the part geometry of this drain and the uh, refractivity of the tropospheric is used for the calculations. So geometrically optics is used along with the two rays ground reflection model. This Longley Rice model is normally available as a computer program that takes as input, and it like transmission frequency, uh, path length, polarizations, antenna height, surface reflectivity, ground conductivity, and dielectric constant, and your diametric uh, your factors. So it does not take into account buildings and the foliage. So you can see Longley Rice basically it is the program, and it need only the input data, and that data is taken how your transmission frequency, transmission transmission path length, transmission frequency, polarization, polarization, path loss, polarization, 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 antenna height, surface reflection, surface surface reflector, sorry, surface reflectivity, sorry, ground conductor and dielectric constant. So does not consider the effect of multipath, building, foliage, and other environmental factor. So Longley's model is failed to include the effect of the multipath and foliage. So it's not giving the appropriate relevant uh, model. So we move towards the OKUMURA model. Now, in this categories, in a OKUMURA model, we will see the outdoor propagations model. The OKUMURA model obviously is best suited for the large cell coverage, and the distances is covered in OKUMURA model is 100 kilo up to 100 kilometer. So in an outdoor propagation model, the propagation is over irregular terrains, and the propagation models available for predicting the signal strength vary widely in their capacity, in their approaches and its accuracy. So as you already seen that irregular terrain model ITS is only cover the frequency range 40 megahertz to 100 gigahertz, and it having the two version. One is the point to point using terrain profile, and another one is the area mode to estimate the path specific parameters. But when we are seeing the OKUMURA model, which is cover a very large coverage distance up to 100 kilometer in urban areas, and it can extrapolated prediction up to 3 gigahertz, and it can be used for specific base station antenna height, and that specific base antenna height ranges from 30 meter to 1000 meter, and the effective mobile receiver antenna height is taken around 3 meter, and this model has been proven to accurate and used to computer simulation tools. The simplified version of path loss model proposed by OKUMURA. It is a simplified version of a path loss model, and this model has been proven to be accurate and used by used by used by computer simulation tools. Computer simulation tools. So it is very simplified version, and for the path loss model, and proposed by proposed by OKUMURA. So its name is OKUMURA model. So for the propagation in an urban mobile environment, for a propagation propagation in an urban area mobile environment. And is express so frequency range is taken from 150 megahertz to 1920 megahertz, and it is the important questions when your question paper is having the multi-choice question. So they directly asked the what OKUMURA model frequency range is like this. So the given the choices, the correct choice is 150 megahertz to 1920 megahertz. So this is frequency range is actually when they are proposed this model. Early our model is approach is not a analytical, it is the empirical in early uh, days. So, so empirical studies are taken into account for developing the OKUMURA model. After that, OKUMURA did comprehensive measurements in 1968, and it came up with a certain model, and he discovered that a good model for the path loss was a simple power loss, or you can say simple power law, where the exponent of frequency, antenna height, etc. are taken into the account, and one of the most widely used models for the signal prediction in the urban areas. So it is applicable for frequency range 150 megahertz to 1920 megahertz, and it can be extrapolated up to certain gigahertz also. The meanwhile, the base station and the mobile station distance is taken into 1 kilometer to 100 kilometer, and your base station height ranges from 30 meter to 1000 meter, and you can see the formula for the urban mobile environment. uh, this is why this is given by OKUMURA developed a set of curves giving the medium attenuations relative to free space, and in an urban and over quasi smooth terrains. So you can say, uh, you can see OKUMURA 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 developed a set of curves so OKUMURA developed a set of curves giving the median attenuation relative to free space in an urban in an urban and over a quasi smooth terrain. The formula is taking L50. This 50 is the free space propagation loss. L50 dV is equal to LF plus AMU. The variables are frequency and the separation distance D, and gain, base station gain factor at the height of the transmitter, and minus gain and height of the receiver, and minus G area. So the L50 dV is the free space path loss. This is the free space path loss. This LF, when we calculate L50 dV, LF is the free space path loss. AMU is the medium attenuation relative to the free space, and this value is can be calculated from the graph. And G of uh, T T of TE is the base station antenna height gain factor, and G of TRE is the mobile antenna height gain factor, and this G area is the gain due to type of the environment which we are using. So recap, L50 dB is 50th percentile medium value of the path loss. This is the 50th percentile median value of path loss. And LF is the free space propagation loss free space propagation 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 and A of mu at F and D, it is the median attenuation relative to free space. It is the median attenuation relative to free space. And this term is base station antenna height gain factor. This is the base station and this is mobile station antenna height gain factor. Gain factor at base station, gain factor at receiver. Now see the some values G of H R E G of H T E, G of H R E at value G of H R E. There are the two values for the HRE. Only one value is the height of the antenna, and it having the formula. There is a formula in the dB scales at log 20 and log 20 log H of TE divided by 200, and this is 10 log 10 log 10 log h of 10 log okay h r e divided by 3, and this is when 20 log of antenna height so it is divided by 3 or h of t you can write here 200 meter and h of r is 3 meter when h of t is higher than antenna. So the parameter of this formula when we where we used is under the specific conditions. The conditions are as पहली the first range is 1000 meter h of t is lies in between 1000 meter and it is greater than 30 meter, and in this the condition height of receiver is less than or equal to 3 meter, or in this formula the range is 10 meter and this is the h r e is and you having a graph, there is two vertical line, two vertical axis and one horizontal axis. So vertical axis is having two different types of notation. The first axis, this is first, this is second. The first is for medium it is the median attenuation. And second one is a so F comma T in E. And here this is the use